morning, good afternoon, good evening. Welcome to GTC. My name is Miguel Martinez. I'm a research scientist at NVIDIA, and with me it is Marian Bendris, who is a Senior Solution Architect Manager, and also Oleg Sudakov, a Senior Solution Architect. Today, we'd like to talk about how to teach an AI to code in every language, and that means to do not only focus on English, but also covering other human languages, such as Spanish, for instance, to focus on not only Python, but other programming languages, in this case, Rust. We will start by explaining the very basics of an LLM, how it works, and how we can use them for code generation. Then we will explain the results of our experiment. We train a code model from scratch, and we would like to share with you our lesson learned. Then we will focus on the different steps of that experiment. We'll explain how to do data preprocessing, how to do pre-training, how to do post-training, and which tools we use for that. Finally, we'll explain some applications that we can do with LLMs, and we will cover some specific focus like speculative decoding and a few other things. So let's crack on. Let's start by explaining how an LLM works. Most of the LLMs we use today use what we call an autoregressive loop. What's that? We have the user input that we call it prompt. For instance, the user input can be a question or it can be just a sentence, such as the cat sat on the. And the LLM, which is represented here in green, what it will try to do is to generate the next token, okay, the most likely token after this sentence. A token is not exactly, it's not a word, okay? But we will explain that later. For now, let's assume that a token is a word, even if we are aware that that's not correct, okay? So for the sentence, the cat sat on the LLM might produce maybe the word mat. The cat sat on the mat. And then we will feed this word back to the input, and we'll try to generate the next most likely word or token. In this case, could be the cat sat on the mat, and maybe is with his friends, whatever. And we keep on generating one word, one token after the other until the LLM considers that it has nothing else to add, or until we reach the maximum content length, which is basically the maximum number of tokens that the LLM is supposed to generate. Let's continue with our previous example. In the previous example, we were trying to generate the next word of a sentence. If you recall, it was the cat sat on the mat, okay? In this case, our input, our prompt will be slightly different. It will be write an efficient Python function to check if the number is both prime and divisible by 5. So this is our prompt, our input. This is what we want the LLM to do. And the LLM can just start writing that function. Okay, we can see here that the next token that it produces is def, is prime, and it produces the code. And that's good. But I will call it reasoning off because the LLM has not been instructed to do anything else but producing the next token. And the next token is the answer to your request. But there is another approach which we call it reasoning on, where we teach the LLM or we force the LLM to produce reasoning traces. Reasoning traces can be kind of the plan that we do as humans before execution and action. In this case, those reasoning traces are between the tags think and think. And in the middle, what we have is the reasoning process, the steps that the LLM wants to execute to produce that code. And why do we do that? Basically because all these tokens that we are producing here are being fed back to the LLM. And that's additional information, that's additional context. And that additional context will help and has been proven to help to improve the accuracy of the results. It will produce better results. So that's why after this reasoning process, the LLM is basically able to produce a more compact, more efficient function. Let's talk now for a moment what is an agent and how an LLM can be an agent. So an agent is just an LLM that has been taught how to use tools. Imagine that the user intent is what is 2 plus 3. So the LLM understands that what the user wants to do is to sum two values, 2 and 3, and has been taught how to use different tools, for instance, a calculator. So it will invoke a Python routine or an external calculator. It will pass the values 2 and 3. It will get a result, in this case, 5, and it will produce an answer for the human in human language. The sum of 2 and 3 is 5. Okay, it can also do other things. It can not only use local tools, but it could invoke a remote API. For instance, it can invoke an API to retrieve the weather in a specific location, or even it can be instructed to talk to other agents. So and we'll see that later in a slide. So the real task of this kind of agents of LLMs is to understand the user intent, decompose the process on different steps, invoke any tools, APIs, other agents, get those results back, and compute an answer. This slide tries to emphasize what we have discussed before, that an LLM, the orchestration agent, can interact with other specialized agents for your task. For instance, imagine that you are a software company and you have a bugs database. So we might have a bug tracking agent which is aware of those bugs that provides useful information when new bugs arrive. Then we also may have, for instance, if we have a very in-house framework, we could have a tech docs agent that is aware of our APIs, our documentation, our style, and will feed back that information when we want to solve a problem. Maybe that problem is solved by a specific coding agent. So we will take the information from the tech docs agent, the backtracking agent, and the orchestration agent will feed the user problem alongside that additional information to the coding agent to try and produce an answer. And maybe the orchestration agent could do something even further. It could double check with the tech docs agent that the coding agent use all the APIs correctly. In the next few slides, we'll see that even if LLMs are able to code in any programming language, they usually struggle to understand and code when they are addressed in languages that are not English. In this example, we'll ask the LLM to write an efficient Python function to check if the number is both prime and divisible by 5. But we do that in Spanish. Our input prompt is Spanish. And we can see here that even the LLM understands the user intent. It gets confused because it produces the answer not in Python, but Swift, and not in an efficient way. And unfortunately, that's not an isolated case. It happens more frequently than expected. For instance, we have another example here which says, write a JavaScript that takes two numbers as input and determines which one is return. And it does it correctly. It produces again Swift code, and there is a mistake here. So even if the LLM is capable to produce some JavaScript code, Python code, it gets confused because we introduce our input prompts in non-English. Hopefully, this is easy to fix, and this is the focus of this session. We'll teach you how to pre-train a model from scratch, how to customize a model to do not only understand English language, but also other human languages, such as Spanish. And we will also make it proficient in not only Python, but also other languages such as Rust. We'll explain you the different steps that are required to do it. We'll start explaining what is data preparation and why it is important. Then we will explain you how to pre-train a base model and how to post-train it with techniques such as supervised fine-tuning. During post-training, we can do other techniques. For instance, we can do direct preference optimization or reinforcement learning, to finally, once we have an extractive model, we can deploy it efficiently for our use. Let's be a bit more specific. For this event, we train a code model from scratch, and we have also created a training lab that you can enjoy it for free during GTC. And because we wanted to make it very simple, we focus on only 3 steps: data preparation, pre-training baseline, and post-training SFT. During data preparation, what we did is we make use of some data sets that NVIDIA have made available for free in Hugging Face. Those are the Nemotron pre-training data sets. We took all of them or some of them alongside with Wikipedia in English and Spanish, and we pre-trained a language model. After that, we took an additional set of post-training datasets, also released by NVIDIA in what we call Nemotron post-training datasets in Hugging Face, and we post-trained that model. And as we said before, that model will support English and Spanish, Python and Rust. And the objective was to do something that you can, or most of the people can do in their companies. We took a relatively small architecture. We based our model in Qwen 3 1.7 billion parameters. This is the details of the architecture. And we trained it from scratch, but not using too many resources for a long time. Our pre-training phase consists of only 0.5 trillion tokens, distributed in 33,000 iterations. And our post-training phase, our supervised fine-tuning phase, consists of 0.26 trillion tokens or 15,000 iterations. We train it on BF16 precision on 32DX A100 servers for 1 day and 10 hours. That can be seen like a lot, but we only use 0.8 trillion tokens. Compared to the original Qwen 3 1.7 billion tokens model that was trained on 35 trillion tokens, that's, I don't know, around 43, 44 times less resources. That's a significant saving. Let's go a bit deeper into the pre-training phase. As we said before, we use the Nemotron pre-training datasets that are available in Hugging Face. Here you can see the different files that we use alongside with the Wikipedia in English and Spanish. And the blend is very simple. We just selected from this dataset, we said that 71% of the content will be code, around 9% will be math, some content will be English and Spanish, and then we also added some supervised fine-tuning datasets. Why? Because empirically, it has been proven that there are some gains if we use SFT content during the pre-training phase that cannot be recovered if we don't do that during the post-training. So if we don't do that during the post-training, we won't get as far as we will do if we do it. So that's why we add it. We save a checkpoint every 500 iteration, and we evaluated the checkpoints every 1,000 iterations on different benchmarks: Human Eval Plus, MVPP, and MVPP Plus. Eval Plus is calculated as the average of these benchmarks, and at the end of the pre-training, we only got around 19.5% accuracy at pass at 1. That cannot be seen as too much, but considering the amount of time that we allocated of iteration, I think it's good enough. During the post-training, we followed a similar approach. We took some datasets from Nemotron post-training datasets in Hugging Face, and we used 25% of the data was pre-training data, and 75% was supervised fine-tuning data. We continued pre-training our previous base model for 11 hours, and we checkpointing it every 500 iterations and evaluated every 1,000 iterations. And this is the results we got. We got, at the end of the post-training, we got around 38% at pass at 1 on Eval Plus. But you can see a different figure here. You can see that after checkpoint merging, we get 38.87% accuracy. What's that checkpoint margin? So to me, it's still like sorcery because basically what we do is we take two different checkpoints, one checkpoint that does really well in human eval benchmarks and another checkpoint that does really well in MVPP benchmarks. And we basically average the weights and that gets a better checkpoint. Saying it's sorcery, but the reality is that that is used more frequently than expected because during the post-training phases, we don't only use SFT, but we also do some reinforcement learning steps. And during the reinforcement learning process, in some cases, some benchmarks that require thinking gets improved, but the benchmarks that benefit from SFT gets worse. So what we do is we continue doing SFT reinforcement learning, SFT reinforcement learning, and at any moment we just merge two checkpoints and get a better checkpoint. While you pre-train or post-train a model, there is a lot of valuable information that you can get from the training curves. Here we have a couple of them, and they tell you a story. You can see here that we started the pre-training, and at any moment during the pre-training, when it finishes, I reset the learning rate. Then I continue doing post-training, and I reset it again to a different value and continue post-training. And those changes can be seen here that they impact the language model loss validation perplexity. You can see here that it evolves really well, and then it jumps the accuracy, and then it continues going down, then it jumps again to continue down until we finish. Why? So basically, because we wanted to show in this experiment how to pre-train a model from scratch. And I think as honest as possible because I didn't repeat the experiment. I made a couple of mistakes. I assumed that the full pre-training would take only, or I estimated 34,000 iterations. But I changed my mind because I noticed that during pre-training, it got improving. So I decided to use all those iterations just for pre-training. And then I reset the learning rate to start the post-training. I could have continued in that specific learning rate, but it was too low. So I just reset the learning rate and I started the post-training phase, the SFT phase. And then when we reached to this number of iterations, I noticed that there was yet some room of improvement. And I did something similar. I kind of changed the learning rate for a higher value, and then it just recovered and continued improving. And those are the spikes. And I wanted to show you, to tell you that even if in a more serious experiment, we usually plan ahead very well how many iterations, we just have one try for this experiment, and we wanted to show what we did to learn from our mistakes or changes during the execution. Before finishing with this section, handing over the mic to Marianne, who will explain in detail what are the steps needed for this, let's have a look to the evaluation results. We can see that the model evolves during the pre-training phase, which is up to here. And then during the post-training phase, it does a significant jump. That's expected and usual. We get to a certain number, which is 38% of accuracy. And we feel that's really good because compared with other models that are trained for 35 trillion tokens, we only use 0.8 trillion tokens, and we get a good model, a reasonable good model that understands English and Spanish, Python and Rust. And that's all yours, Miriam. Thank you.
Thank you, Miguel. Let's now dig into the techniques used to train the LLMs powering Code Assistant. And let's start with the data processing. Data preparation is a critical step as the quality of the data directly impacts the quality of the model itself. So here in this figure from the Nemotron CC paper, we can see the impact of data curation on the accuracy of the model. So it shows the MMLU score for an 8 billion parameter model trained on 1 trillion tokens. And as you can see here, so it achieves actually a higher MMLU score using a higher quality subset of tokens with the Nemotron CC HQ, high quality. And what we can see also is that the model can achieve similar results with 4 times larger data sets with the Nemotron CC pipeline, allowing to retain more high quality content from the DCLM while still cleaning the data. So this highlights how data quality and also data composition are very critical in model performance, especially when training models over very long training settings. In general, data preparation involves 4 main steps: cleaning and data filtering of the data, then deduplication to reduce repeated content, then setting the data blending strategies, meaning how we can combine different data sets to create a balanced mix of different capabilities, such as programming languages understanding, function calling, instruction following, and so on. And finally, the tokenization to prepare the data to be consumed by an LLM. So those 4 steps can ensure that the training data is clean, diverse, balanced, and ready to be consumed in an efficient training setting. So let's dig into them one by one. So data cleaning and filtering consists in removing low quality content, noise, and safe content to ensure we start with a reliable data sets. So to do so, we usually start with very basic text reformatting, basic cleaning, fixing some issues such as like bad Unicode characters, broken new lines, or repetitive text, for example, that can appear very often on web datasets. The second thing that we can do is document level filtering. Here we remove low quality content using several approaches, such as like a classifier based quality filtering scoring, where we evaluate things like accuracy, clarity, coherence, grammar, or overall usefulness of a document or a paragraph. We also can apply some heuristic filters to catch any obvious issues. And finally, we can perform some data classification to remove, let's say, personal information, or classifiers to detect domain, toxicity level, or complexity of some of the documents. Several deduplication techniques can be applied, from lexical deduplication, including exact deduplication or fuzzy deduplication, which consists in identifying documents that are not exactly the same but very similar. Techniques can be used like min hash, for example, for that. We can perform also semantic-based deduplication, where we use some sort of embedding representation to detect documents that are semantically similar, even though the words and sentences are different. And finally, we can apply task decontamination. This is really important to ensure that training data does not contain any content from the evaluation benchmarks. And since LLMs often have strong multilingual capabilities, we can also apply task decontamination across languages to ensure a fair evaluation of the trained model. All those steps from data cleaning, filtering, and deduplication can be done at scale in an efficient way using NVIDIA NeMo Curator. Let's now talk about the data blending, which consists on combining multiple sources of training data to create a dataset that is diverse and balanced enough with high quality. So we really need to carefully choose this mixture because it strongly influences the skills and the behaviors the model will learn during the training. So for instance, web data will provide general knowledge, while code data sets will improve programming capabilities. So here in this slide, you can see an example of a pre-training data mix from the Nemotron Nano v3 paper, where different data sets are combined in specific proportions. Notice it is also very common to include small set of supervised data sets in the pre-training phase, such as reasoning and instruction following, to help the model learn useful interactions in the early stages. We highly recommend to get inspired by already published data blending. Generally, they are a result of a few ablation studies to find the right data blendings for the targeted use cases. And in Miguel's experiments, we wanted to make the model good in understanding human languages such as English and Spanish, but also on Python and Rust programming languages. And this is why more than 70% of the data was Python and Rust code, while the rest of the mix was a mix of math, English, and Spanish datasets. And finally, the tokenizer. Tokenization converts raw text data into tokens or subwords, the unit that a language model actually processes. So on the right, you can see some examples using the quencoder tokenizer across two languages, English and Spanish, and also programming languages Python and Rust. So efficient tokenization is important because it reduces the number of tokens that are needed to represent a text, which directly impacts the inference speed and also the context length utilization. Both are very important for Code Assistant. So while tokenization may seem like a small step, it actually plays a key role in making LLM scalable in applications. So if you are training a model from scratch, it is actually useful to consider training a tokenizer that is adapted to your specific use case. And that is what Miguel showed in the LLM training experiment section. Once we have our tokenizer, and prior to the model training, we usually convert the entire training dataset to tokens for efficient training. So in this slide, you can see a link to Megatron Bridge tutorial for the DCLM dataset preprocessing, including shuffling, tokenization, and conversion into a binary format. Okay, let's now focus on the pre-training phase. So pre-training phase is where the model builds strong capabilities of language understanding. During the pre-training phase, we use a massive amount of unlabeled data, mainly raw text data, to train a neural network to predict the next token. So it is a quite simple loss function, but it's quite essential as it builds the model's core capabilities for language understanding, but also knowledge acquisition. Pre-training is usually the most data and compute intensive, and it results on a foundation model that we usually call a base model. Also, it is common to leverage existing foundation models instead of training from scratch. We can add the new capabilities by taking a base model and continuing in pre-training that model on a new domain using the same loss function, which is the next token prediction. And in this case, this process is called continual pre-training or CPT. Usually pre-training is followed by a long context extension phase. Especially for Code Assistant, this phase is quite essential to equip the model with strong capabilities for understanding complex code base and reasoning over extended content. In long context pre-training, the model is trained on a very long sequences of text to predict again the next token. This allows the model to capture dependencies across large passages and documents. This is especially critical for Code Assistant as it enables the model to understand function calls across files, track type of definition, constants, configurations, and offers more accurate refactoring suggestions. Okay, code completion is a special use case for Code Assistant. So to include this capability to an LLM, we can use the fill-in-the-middle approach, or called also FIM, where the model learns to generate missing portion of the code from the middle of a sequence, rather than only predicting the next token. And to do so, we can actually transform the same large enabled data sets used for pre-training by moving a code snippet from the middle of a document to the end, and using specific tokens to indicate prefix, suffix, and mid snippets. If you are interested into the theme approach, you can check the listed paper here in this slide, exploring ratios of theme versus regular left to right datasets proportion during the pre-training so that the model can gain infilling capabilities without losing its core capabilities of generation. Okay, so once we have a base model, let's dig into the techniques that we are using to align that model. Mainly, we call it post-training phase. Okay, starting from supervised fine-tuning or SFT. This phase where the pre-trained LLM is trained again, this time on labeled datasets to follow explicit instructions or perform specific tasks. So for code LLMs, for instance, this typically will involve code snippets paired with desired outputs like code problems and their solutions, doc strings, and so on. And SFT helps the model to align its behavior with the developer intent, for example, improving the accuracy, the relevancy, and the usability for real-world use cases. Another technique of post-training is preference alignment, which is the process of fine-tuning an LLM to match specific preferences. So for code assistant, for example, this ensures that a suggestion follow best practices, maintain consistency, and prioritize solutions that developers are most likely to accept, and so on. So example of approaches that can be used are DPU for direct preference optimization or reinforcement learning such as PPU for proximal policy optimization or GRPU, group relative policy optimization. Okay, if you are not familiar with reinforcement learning for LLMs, so this slide shows the principle of RL in LLM words. So this includes a state, which is a user prompt. Here, for example, we are prompting the model to solve an equation, a math problem, for example. An agent or a policy here, which consists of the LLM usually. The action, which consists in responses generation by the LLM, and a reward model that scores basically how good or bad each response is. And the idea here is that we are going to train the policy or the LLM basically model to maximize the reward. And when models' output correctness can be mathematically or logically verified, we can actually replace the reward function with a rule-based reward. And this is what we call verifiable reward or RLVR. This is actually extensively used as post-training technique for programming language models, where we can use unit tests and compilers as a reward function. Actually, in the natural, RLVR teaches the model not only to generate code that looks like code, but actually code that actually runs. Okay, so to summarize, here is the list of training approaches going from pre-training and CPT to supervised fine-tuning to preference alignment. So pre-training and CPT purpose is to add language understanding, factual knowledge to the model. It requires raw text data, and usually it's quite easy to gather and collect high quality data for that. And some of the consideration is to do some experiments to find the best data blending for that phase. On the other side, supervised fine-tuning basically has as a purpose to incorporate instruction following, chat, reasoning capabilities to the model. So the data type that is required for SFT is usually prompt and labels or answers. And some of the advantages is usually quite simple and stable to train. However, one of the considerations is that it is very hard to collect a good quality annotated data for SFT. And if we dig into the preference alignment, so the idea here again is to improve some of the capabilities and to align them with human preferences. The type of data sets that we need to collect is prompt answers and reward or ranking for those answers. So There are several advantages, and one of them it's usually applied after SFT to fix any behavior that were not covered by SFT. And the data sets are usually easier to collect compared to the SFT part. Now, digging into the techniques, DPU, for example, it's not really a reinforcement learning technique as there is no reward model. It directly targets human preferences and it's quite fast for as an alignment technique. PPU needs more additional models. It is sensitive to the training and it can be computationally expensive, while GRPU basically offers a much more efficient computationally algorithm to the PPU. And some of the post-training techniques, such as supervised fine-tuning and all the preference alignment, can actually be applied in fine-tuning the entire model or in fine-tuning it in a parameter-efficient fine-tuning regime, which consists in adding extra parameters that only those parameters will be fine-tuned within those settings. Okay, let's now have a look at some of the NVIDIA tools allowing to train such large language models. Let's take a look at the NVIDIA NeMo framework. It covers building speech models, vision foundation models, VLMs, and LLMs. NeMo Curator, for instance, provides accelerated library for dataset preparation, and Megatron Bridge provide efficient large-scale distributed training. Megatron Bridge is based on Megatron Core backbone, an optimized library focusing on pre-training, CPT, and SFT. Auto Model is based on PyTorch implementation, offers day zero support for Hugging Face models. And for post-training, NeMo-RL supports reinforcement learning algorithms, while NeMo-Gym offers the standard environments, orchestrating policy generation collection, defining tasks, and verification logics, for instance. And for deployment, NeMo supports optimized inference pipeline, evaluation, as well as guardware. And all those components offer a complete ecosystem for developing advanced AI applications. And in the experiment showed by Miguel, we use NeMo Curator for data processing and Megatron Bridge for pre-training and SFT. So let's have a look in the next slides on how it works exactly. Megatron Bridge training recipes idea is to provide a ready-to-use and optimized training workflows. So recipes are pre-configured set of hyperparameters, optimizer settings, parallelism strategies, precision configuration that are designed to streamline large-scale model training. So you can start, for instance, by instantiating a recipe, for example, SFT of Quen model, and directly override certain parameters to fit your desired setup. So this example shows how to load the pre-training recipe of Quen 3 1.7 with Megatron Bridge and simply launch the pre-training on the provided data. So we simply import the pre-training recipe for the targeted model, as well as the callable forward-backward steps, and also the training pipeline, here the pre-training. And then what we can do is we can override some of the pre-configured hyperparameters, such as data path, for example, here. We can provide not only the dataset list, but also the corresponding blending. We can specify the number of iterations, for example, here 150K steps. And we can specify the global batch size, for example, here. And finally, we can simply invoke the pre-training pipeline using the configuration. If you need more detail, have a look at the documentation in the link provided below. For context length extension, we simply need to do exactly the same experiment than the pre-training, while we need to provide a link to resume from a checkpoint, but also set the new sequence length here. It's shown with 32K sequence length. Finally, for SFT, we need to load the Quen 3 or 1.7 SFT recipe, as well as the fine-tuning pipeline. We need also to specify whether we want to run the full fine-tuning of all parameters or using parameter-efficient fine-tuning, such as LoRa, for example, here. We need also to specify that we want to resume from a checkpoint, the base model, for example. And finally, we can simply invoke the fine-tuning pipeline here. Okay, we have seen in the introduction section that LLMs are powering applications for code assistant. In this section, we will explore some techniques to efficiently use LLMs to build code assistant beyond classic LLM latency and throughput optimization, such as quantization, KV caching, and agentic workflows. So first, let's have a look at the LLM at inference time. An example of techniques that we can use is called structured decoding or guided decoding, which constrains an LLM to generate within a grammar-aware tokens so that only synthetically valid tokens are allowed during the inference. So this diagram here shows the syncode paper. It shows a grammar-based lookup to ensure generated code strictly follows programming language grammar, reducing syntax error in outputs, as shown here as an example for Python generation. Several inference libraries such as VLLM or TensorRT-LLM offer guided decoding capabilities supporting regex, JSON, or grammar-based structures. Another inference optimization technique, and not only related to code assistant, is speculative decoding, which consists in using a smaller model called a draft model here to generate multiple future tokens, and then the larger or the target LLM verifies them in one forward pass. So the draft model generates multiple future tokens, typically 3 to 12 tokens, and then the target LLM would evaluate the drafted tokens in parallel to see if they match. And any tokens that doesn't match is basically rejected. And from the point where there is a mismatch, so the system resumes a standard token by token generation, which will ensure basically that we are always having identical generation to classic decoding. And frameworks such as TensorRT LLM supports speculative decoding and can significantly boost the throughput. Sometimes we see over 3x improvement without sacrificing the quality of the generated output. So if you are interested into speculative decoding, I recommend to have a look at the blog listed here. So finally, we wanted to finish talking about autonomous systems. So a core capability of autonomous systems is the ability to evaluate and improve generation without human interventions at all. So an example is a self-debugging approach, for instance, that uses an LLM to iteratively identify and fix errors on its own generated code. So instead of producing a single answer, the agent can generate code, execute, analyze the failures, reason about the errors, and iteratively refine the solution. And this graphic here shows an example from NeMo Agent Toolkit with a code agent that generates code, run unit tests in a sandbox, analyzes failures with a reasoning model, and iteratively fixes the code until it passes all the tests. And here is how it works. So let's say, for example, we have a problem statement, for example, a GitHub issue. A code LLM, similar to the one that was introduced on Miguel's section, could generate a Git patches that attempt to fix the issue, but also maybe unit tests, for example. Then in step 2, the patch code is executed against the unit test in a sandbox environment, for example. So if the tests fail, we use a reasoning model to reflect, analyze the output, and suggest potential fixes to that. And we can iterate until we reach all the unit tests that are passed. So we see the emergence of this type of techniques moving us from developing code assistants toward more autonomous code agents. And with that, I will give the mic to Miguel to conclude our talk.
Thank you, Miriam. I feel it's time to wrap up. For the last 45 minutes, we have tried to demystify the process of pre-training a model from scratch, how to customize it, and we have gone from the very basics, from how the autoregressive loop works, to how to use the most complex reinforcement learning tools to achieve this. The good news is that this trip doesn't end here. We have also created a lab, a hands-on lab, where you can practice with different notebooks with the code that we have created to showcase this one. I do really encourage you to have a look at it because there are a lot of recipes and examples that you can use on your own use case. And I think we are done. I would like to thank you all for attending this session. We'll remain for another 40 minutes in the chat, so please do submit your last questions. Oleg didn't present during this session because he has been answering questions in the chat, so thank you, Oleg, for that great work. See you around the GTC. Bye.